mathematician and an educator.
Oh, thanks, man.
And he is going to talk about mathematics, law, and the taxonomy of studies, or what's wrong with modern math.
Hey.
Okay, so.
Yeah. Oh, sorry. Yeah, Curt, go for it.
It was really important that Michael came because he's the only person nerdier than I am.
Yeah.
All right, so. Wait, you're not going to get the microphone now that you gave it to me. So it was really important. It was really important he came because one of the things we do is we've shown everything from mother to family to the morale, but what I want to show is in education was that the science applies in education too. And Michael has done phenomenal work in this. Anyway, so thank you for being here, Michael.
Curt, it's an absolute honor. Curt, very early on in the presentation said, what was it? Is there anyone crazy enough in this world to want to try to unify all the sciences? And I raised my hand immediately before he had finished his sentence. And I felt, I always feel a little bit of a tinge of like envy because he got there first. But he also saved me 50 years, and I don't know if I have 50 years left. So, Curt, I love you, and I bless you for what you've done for all this work. So I'm going to try to take it and run with it. Brandon, Luke, Noah, and anyone else, your talk, Dr. Brad, great talks. Brandon, I'm going to try to make this light and funny. It's after lunch, keep things moving. I got a lot of slides to get through. Do interrupt if you need me to interrupt. A lot of this might go over your heads because I'm talking about mathematics. I'm going into my own little cone of autism here, and but if you like go out and get a beer or go downstairs, it's fine. I'm used to it, So it's they're not paying me for this. It's fine. I don't know. And also, if you don't like math, the good news is this talk will. It will end. It'll end at some point. All right, so.
Get on this side so we can see your face.
Yes, sir. Should I be in the comedy room, kind of?
You are already there.
Oh, yeah.
You're already there.
You already did it, bud.
Well, let's see if I can make the clicky work. Okay, well, this is me.
Oh, my God.
Yeah, that's me. I'm going to have to read off the screen a little bit, but I've been a professional math tutor for 20 years. Everything that we do here is data-driven. I'm a data-driven educator in the sense that I've got a pretty wide base of anecdotal evidence that's statistically robust, over 1,000 students, 700 boys, 300 girls. I don't have a formal math degree. I'm I'm self-taught. I was an English major in college. But my claim to knowing math is that when I was 4, I was introduced to what a triangle was in preschool. I'd already known what a triangle was. So I concluded, when are we going to learn about all the grown-up shapes? Because if we're learning about triangle in preschool, clearly, my mother and father at work, Johnson, what is this? It's a 20-sided shape. It must be so that's what I thought grown-ups did when they went to work when I was 4. That was all that was literally what I thought was going on. And I'm still learning what the grown-up shapes are. And you'll learn what some of them are in this talk, because Curt has actually helped me figure out what are the most grown-up shapes on the planet. Also, I study epistemological blockages. Like when I work with kids, I'm so fluent in math that I don't have to focus on it. It's like driving a car very fast, and I mostly focus on what's missing in their epistemology. Why can't they, what priors are they missing? Or what priors have, I'll just say leftist educators messed with, so that they can be told what they're seeing before they experience what they're experiencing, which is what I mostly cure kids of. I talk fast. All right, so redesigning the academy to conform to natural law. Me, is shaking hands with Pythagoras. Why do it? Well, because we can. Curt has shown that if you watch his videos where he goes down the rabbit hole. I'm of the view that we're going to need people to be sympathetic to our movement who don't grok it or get it in the way that we would get it, but they would be sympathetic to it. I think that there are people in the academy who are largely just looking for a paycheck and a steady job. They're in that sort of a group of people. I'm not one of them, but we want to give students tools to solve new problems rather than reference old ideas and puzzles. This is a very common problem in math education, is that you give them a textbook of problems and they're all composed problems. I'd rather take a child through the building of a house. Even though I don't know how to build a house, I'd rather take them through the building of a house. And every time they need to figure out how long something is, you introduce the Pythagorean theorem. You give them hands-on experience, and then you bring out the math. I like to call math Tinkerbell. The best mathematician of the 19th century, Carl Friedrich Gauss, called Math, the Queen of the Sciences. Notice the feminine there. I think Tinkerbell is kind of like Peter Pan's friend who pops in when he needs some assistance. You bring the math out when you need it, and then you put me back in the drawer when you don't need me to talk anymore, which is what you're probably going to be feeling in 5 minutes. So, so the Academy, I already talked about this stuff. Can you read? You can read it. All right. So, when we remove bias, error, conflation, non-testimonial epistemology from all academic subjects, what's going to happen? What subjects are going to survive? That's what I'm going to attempt to address in this talk. The idea of taxonomy of studies is, can we create a periodic table of all possible academic subjects? Why would we do this? Well, first off, the core problem, Martin did a great speech. I forgot to mention you, Martin. You really teed me up here because the core problem in all of academic discipline is that we use analogies and metaphors, which inflates, it makes it easier to learn something because it makes the subject relatable and meaningful to you because you can personalize it. But unfortunately, that intuition doesn't scale to higher and higher problem sizes. And so you can read it. Most academic subjects, they don't measure things properly. I mean, I got that from Curt years ago. Curt fixed my epistemology about 5 years ago, and it's still blowing my mind when I'm discovering every day. But you can see it up here. I think Martin alluded to this. You either add too many dimensions, so like, I don't know, I don't want to name them, but like blank studies, any college course that's called blank studies, it's in-group signaling. We know that now. It's demonstrable. Literature, I think literature is a great subject. I was an English major, but unfortunately there's too much freedom in how we measure the worth of a work of literature. And so it devolves into, this word ochlocracy means mob rule, which I think is a better word for what we call democracy today in America. It's really an ochlocracy. History, all stories convey facts, but they also convey meaning to people. There's shared meaning, the in-group signaling again. Or our subjects lack relevant dimensions to fully account for causality. So mathematics is sort of placed at the top of the pyramid of the academic subjects, but yet it doesn't have enough data to actually teach you anything except about structure in the abstract. Philosophy and ethics, they lack the first question, right? When I blank you and take your stuff. And political or social, quote, science, anytime you're in a subject where you're just deriving conclusions rather than inductive reasoning where you're taking in data. And here's another thing that I don't think anyone's ever brought up. New subjects are being invented every year. I keep track, just like Brandon keeps track of all the smart people working within the context of law, the thought leaders, I'm keeping track of the mega nerds of this world. I'm sort of an information trafficker for a living. The new subjects are being invented every year. This is a process that used to take decades. But we don't vet or curate the creation of subjects except politically now for technological purposes. So if it can make somebody a buck, if it can tilt voters in a direction, or if we can just, expand hedonic utilitarian. Yeah, go for it.
So are you saying that, I love what you're saying. I love everything you say. But so what you're saying is that these new subjects have meaningless measures.
These new subjects are going to actually be meaningful, but we haven't invented them yet. So like traffic flow is now a major you can take in college, but that used to just be like math and common sense.
I had you in verse, thank you.
Thank you, yeah. So I mean, I'm expecting with the AI revolution, we're going to be introducing about one subject per month. And these subjects, I want to be clear on this. This subject knowledge will be implemented. So this is the only unfunny thing I'm going to say in this whole talk, so I'm serious right now. Thank you. Please never do, Donald Duck. But this new subject will be implemented. The wizards in their ivory tower living in the cloud city, they are going to be, well, you can see it, traffic flow, stoplight patterns, airplane flying, logistics, shipping, robotics, social justice. They're going to implement it, and they're going to use AI to implement it as much as they possibly can. And you will feel the impact of these new subjects that are being invented, whether they're real or not, whether they're inflationary or deflationary, and there's no escape. You can't run from it. So what I want to do is I want to create a periodic table of subjects in the academy so that when a new subject is introduced or when a sub-subject is introduced, we can say, is this valid? Does this comport with natural law? So how do we classify or taxonomize a new subject? In the past, we mostly did it through guilds and cohorts. There were like majors and areas of study. These majors developed because of historical necessities that different people faced, and they also tend to cohort based on IQ. Curt made the point that if you just spend $150 on an IQ test and a personality test, you can dispense with a college education to know where to put yourself in the workforce. And I think that's a better trade to spend $150 to know where to put your kids in the workforce than to trade your retirement for their entry into the workforce, which is basically modern day bondage as far as I'm concerned. And it's employee centric. It's like, let's keep the college professors happy. I didn't make them happy. I asked them too many questions. They didn't know what to do with me. They didn't know where to put me. They just bounced. I was like an orphan in college. I just bounced around from major to major, kicking ass in all of them, and then, what's the point? So I don't want to be a part of the Brahmin caste, even though I'm sort of genetically inclined for it. So we got to switch it to operations. We got to make every subject compatible with operationalism. You have to be able to understand that in any subject, when you make any chain of reasoning, that chain of reasoning is not just cost-free logic. There's a step-by-step-by-step sequence, and every time you make a logical deduction, there is a cost somewhere that is either being acknowledged or not acknowledged, and we have to make all those costs known and visible. We have to bring it all to light. So the other thing that's important, I think, is that this idea of a periodic table of subjects is generalizable. There are elements in the periodic table that weren't discovered until after the concept of a periodic table were invented. And then they knew, oh, we're missing element 43, we're missing element 57, we have to look for these things. Maybe they're in a mine in Sweden. So maybe there are subjects we haven't covered yet, that have to do with natural law and so forth. And maybe I think there's a particularly rich interplay with Germanic versus Anglo ethics, where there's still, I think, undiscovered subjects that, anyways. So yeah, how can we transition our schools and students? Oh, whoops! Oh, we want to turn it into this. We want to go from this to something more like this. Notice that the mathematician is way down here. That's Archimedes way down here with the kids, whereas Big Daddy Aristotle, like you, Curt, is up there. That's Curt and Martin. That's Curt and Martin arguing. This is Curt and Martin arguing. And as Curt always says, if you look at Raphael, who made this portrait, Aristotle is just ever so slightly taller than Plato, which is both physically and I guess metaphorically true, and that's what Curt always says about Martin. Just trying to throw some sauce on you, Martin. All right, so how do we, is there a way to subvert academia from within? I think there is. I'm not saying this is going to work, but it's what I'm going to try to make work, because I have to work in education, and I have to play nice with the academic system. So I say the Trojan horse is mathematics. Beware of Greeks bearing gifts. The Greeks invented modern mathematics. So they gave us a gift, and we can re-gift it back to the academy, is my attempt. Most subjects reveal traces of physics envy. If you look in any college campus, if you ask around who's the smartest people in college, and they're going to say like engineering or physics or math, and whether that's true or not, and even though it's a narrow cone of competence, it's a proxy IQ test. Like I said, we're spending way too much money just to give people IQ tests and know what work to give them. Math is sort of given a gold standard treatment, even though we both agree that it should be computer science at this point.
That's a very complex topic.
Very complex topic. Not going to talk about it today. I had to cut like 8/10 billionths of my talk to fit it. It's a math term, infinitesimal. Math has always been taught in universities also. I think of it as a legitimizer.
Yes.
It's like, well, if you know math. And the reason is that math really devolves from astronomy, and astronomy is calendar making. So, back in the day, the priesthood caste had to be able to predict the seasons, and so all of this quadrivium stuff sort of emerges from that, with music being a sort of happy accident of your ear and your brain. Proofs and logic, argument, yeah, you get that stuff. Yeah, go for it.
Gloss over my favorite subject.
What is this? What?
Proofs and logic.
Okay.
You were just dismissive.
Nah. Well, I do it. I'll definitely waste time on proofs and logic, but especially with you, pal. But no, I think that's important. The idea is that I'm going to make the case that I think proofs in Greek philosophy actually came from legal arguments, because if you have to prove, did your two sons inherit an equal amount of land? Well, the Pythagorean theorem guarantees that if you have a piece of land and you can put a right triangle somewhere in it, then all the land over here plus the land over here is going to equal the land over there. That's a squared plus b squared equals c squared. So it settles a legal argument. So a proof is really useful when you can't actually go out and make the measurements. It's too expensive to make measurements. So you rely on indirect reasoning to save you a lot of time, energy, and money. So I think that's the real value of a proof. It's a prediction that should be true, but as we know, you can't scale your intuition, so it doesn't necessarily apply to other contexts. So I look at it as math. You know, there's this guy down here. I don't know if you know this dude. This is what is this? Ronald Reagan. And he, Ronald Reagan, you know, it's like he's treated as like the smartest guy ever because he is like sticks his tongue out and he knows that 6 minus 3 is 6. But I'm not a real fan of him that much, even though he taught me a lot back in the day. But I think it's because the idea is that we're teaching kids to justify their reasoning, and that's what proofs teach the average kid. They don't teach them to be rigorously logical and like industrious in your attempt to falsify your reasoning. It teaches you to try to justify how this one triangle overlaps this other triangle. I don't think that's the right way to be teaching kids. I think they should be learning computer science to try to construct solutions rather than justify them. So anyways, I'm saying that math is the basis of my proposed re-taxonomy of the education system. So we got to start with what's math. Well, Aristotle would say the functionalist argument. You know, a man is his function. So what a thing is its function. So the old answer is you ask a mathematician. A mathematician is someone who converts caffeine into theorems. Pyle Erdos, very famous, not famous, mathematician in the 20th century. But that's not that helpful. It only tells you what they're paid to do. It's only what you see them doing in universities. And I do it unpaid. Many other subjects also convert caffeine into theory. You know, a theologian converts caffeine into theology or divine theorems. A philosopher converts caffeine into moral theorems. A Marxist converts caffeine into social science. And a neoliberal converts caffeine into political science. I don't think I need to explain that.
No, it should say pseudoscience.
Pseudoscience, sure. Sure. Anyways. All right, so what is math? You should ask me. I know. This guy knows. Just kidding. You just have to operationalize the subject. Like I said, it's going to get a little technical. Go grab a beer if you want, or whatever. Let's operationalize it. So what's a number? Numbers are not abstract, guys. Numbers are stones. The word calculus or abacus is Greek and Latin for stone. Okay, so any number that you see, like pi or whatever, it's representable as a pile of stones or several collections of stones. So when you count things, you place stones into a bucket or into a pile. We call that a set in set theory and mathematics. Addition means you combine the piles. Subtraction, you get the deal. Negative numbers are holes in the ground you can kick a stone into. And 0 is just the ground. 0 is not nothing. 0 is the medium of exchange in which you're performing exchanges. Math abstracts that out because there's no need to provide a meaning or a provenance to the idea of 0. But in operational terms, 0 is the ground on which you're doing the counting. So 0 is never nothing. It's just nothing is being counted at the moment. So yeah, math is not abstract. I want to bring up this definition of these Greek words, nomos and logos. Anyone familiar with those words, what they mean? Nomos is basically the idea of rule of law that is customary, whereas logos is the idea that the law is derived from logic and reasoning, continuous recursive disambiguation down into first principles. So when people think that it's the law to, you know, get the clot shot or whatever, that's just people's opinion. That's in the realm of doxa in Greek, or opinion, and it becomes nomos, or just custom. And custom is not bad. Norms are not bad, but they're not necessarily questioned and optimized for what we're trying to do. And Curt and Brandon and all these guys have figured out all these different ways to apply the law and bring it back into our lives. So yeah, it's always been a pile of rocks, one astronaut to another. Always has been. All right, so math is not abstract. It's not. It's a lie. So when you operationalize it, also just some more technical stuff, a rational number like a fraction, it's a conversion of one pile into another. 7 over 5 is 7 of this for 5 of that, or you know, you need a knife to cut the rocks into fifths. Irrational numbers are where each decimal place represents an amount of exponentially smaller grains of sand. So if you could refine the sand to infinitely small size, you know, you have the decimal expansion of pi. I wrote the decimal expansion of pi on the chalkboard here. In the old definition, it's a bunch of digits that kids try to memorize to sound like they're smart. So I put all the digits for you and just saved you all the time of memorizing them all. Whereas the new version of pi is geometric. It's operational. If you had to take a line through a circle, how many of those lines would fit around it? It doesn't matter what the number is. It's just, can it fit? How many of those fit around? Operational equals balances the scale. This pile counts the same as this pile, or this pile weighs the same as this pile. They're two different things. I got this next one from Gordon Brown, who wrote a book, The Laws of Form. Gordon Brown was a graduate student of Bertrand Russell. And the word equals actually means is confused with. 2 plus 1 is confused with 3. You can't really tell the difference if they're all in the same bucket. So math is is about not being able to tell the difference between things. That explains the confusion, I think, in a lot of academia. Because wherever academia is looking to math for its epistemology, well, math says proper epistemology is confusion. That was a joke. No, it's not a joke. It's actually true. So I think that explains a lot.
The thing is, it's actually
Crazy true when you see it.
Well, you're covering very profound things.
Yeah, it's a lot.
No, it's brilliant. I mean, I love it, but I mean, when you say it, it sounds funny, but it's actually true.
Yeah, I spent my whole life studying confusion. That's it. Dun-dun-dun. Noah, and you have it. I've maladapted in certain functional ways. I can always get a job. So I think the confusion in academia, let me try to make this a little more concrete. When children or immature adults try to justify their legal rights, like I have the right to freedom from fear, as FDR once said, that he's conflating a freedom, which is the ability to choose your own employment in a system, with now a government protection that police have to be marshaled to your defense so that you feel something on the inside. So justificationary reasoning, which works in mathematics because it's a context-independent language, does not work when you add context. So I'm going to talk about how do we add context to the subject of mathematics and turn it into all other possible subjects until we get to one at the end, which I'm not going to tell you what that last subject is until the end. You might figure out. You might have. No. I'll go fast. And then there's just, there's some other things if you're going to operationalize math. This is more esoteric. I'm not going to talk all about it, but you can kind of read it. The slides will be up on the website. I want to cut on the time, but essentially, all numbers store measurements that are regarding geometry. Yep. The only sortable data states are actually binary numbers, zeros and ones, ups and downs on a magnetic strip. We can only store pi, e, or square roots via algorithms to arbitrary precision. So we have to, if we want to make the algorithm always work with pi, we have to make the computer plug in the decimal number, but then make the error correction necessary, because when you use that too many times, the errors start to accumulate. And then the video game, when you're rotating the video game, all of a sudden the characters are off screen because pi there's been errors in the decimal approximation of pi. But you don't need to do that much, actually. You only need, I think, 29 decimal places of pi to calculate the circumference of the universe to within one Planck length. So we don't need that much precision, actually, for practical purposes. So why do we go down this rabbit hole in mathematics education of teaching people all this theory and idealism? So we're going to talk about that. Also want to just talk about it. Anyone ever remember imaginary numbers? You ever learn about that in high school? You have to go sit through factoring polynomials and you're wondering, why do they care that I find all the false solutions to this equation? Great, wonderful. From a computer science perspective, every video game, how many of you guys have ever played video games? Okay, imaginary numbers are essential to all video games because if you want to rotate in a sphere, you have to create a vector that multiplies by itself to equal -1, or really any negative number. So introducing a fake number called I squared equals -1, if you plug it into an exponential function, some people know what that is, don't worry if you don't, it allows the camera to rotate seamlessly with basically lossless updating, lossless error resolution. So you kind of learn that at the end of high school, but what you don't learn is that the exponential actually has 3 possible imaginary number components. There's the spherical motion, there's linear motion if you make your imaginary square to 0, and there's actually hyperbolic motion, which is on this silly surface here that I hope none of you never want to be on a hyperboloid, folks. Never golf on a hyperbolic golf green, because if you miss by like a tiny fraction of a degree, the golf ball is going to go 2 miles away, because errors are magnified on a hyperbolic surface. Whereas on a sphere, if your golf green is a sphere, if you just hit it hard enough, it'll eventually roll around and eventually go in the hole. So that's important. All motion along any smooth manifold, Curt brings that word up. Any space with coordinates can be described by these exponentials and with imaginary numbers. So this is the technology that makes all the video games work. And why don't we just teach kids this stuff? Because they're already playing these games, and then they get introduced to this is basically like junior year college mathematics. Now we wouldn't necessarily teach that to all the kids, all of the stuff, but the basics of it, they learn how their video games work. I think that's pretty cool. Another concept I want to bring up is that Curt brings up dimension a lot in language. If we teach math, for example, the idea of a zero-dimensional concept or a number is stones in a pile, but we haven't ordered them. So you just have a bunch of stones in a pile and they look the way that they do, but you haven't counted them yet. To count them, you have to put them into one dimension or in a line, ordinal logic. 2-dimension would be stones in a grid, 3-dimension stones fill a volume, and in 4 dimensions and so forth, we have to get a little more abstract, but we can still draw them. We can draw them as flowchart diagrams, which I'm going to talk about.
You can just draw them as time, too.
You can draw them as time. You can draw them as time, but what I've let me see if I can get there. What I found it better is that when you draw higher and higher dimensions. So the idea here is that when we learn math, we learn it to correspond to our intuitions, like moving through a particular space. But when you go to data sets, which have like maybe 90 different variables, you're looking at a 91-dimensional system. It's very hard to visualize a 91-dimensional system. I've tried. Never try it. Now you know why I am the way I am. So the idea here is that we can only understand these dimensions ever so much, but if you want to try to understand how do you create a higher dimensional space, just take any shape that you're looking at, add a point to it, connect all the previous points to the new point, and you've actually upped the dimension. In fact, if you start with a triangle and you build a point above it, you get a 3D triangle. You build a point outside of that. It's still in 3D, but as a flow chart, you've now introduced 4 different distinct axes, ordinal axes of measurement. So you actually have a 4-dimensional triangle when you keep adding points to a tetrahedron, 5, 6, 7. So new degrees of freedom. Anyways, what we're getting at is that originally we learned math to correspond to geometry because geometry corresponds to our intuitions, how we move through space. But the big boy math, if you will, what I was seeking when I was Donald Duck as a kid was actually these diagrams here, which doesn't look at all like physical space. This looks like, I'm in the bowels of some computer science class trying to figure out how do I go from 1 to 4 or 3 to 2 or how to get my taxes. Like this might be like I have to get my taxes paid. This is like the government, and I'm trying to figure out how they can move through the system, and I still haven't figured out how to do it. But the idea is that a space or a continuum, this is a key concept. A graph, these things are called graphs. How we model space as a continuum is actually a graph that's like a grid. You can see the grid on the floor. There's the floor tiles with the different dots there. If you could make the tiles smaller and smaller and smaller without changing the geometry of the grid, that's what the continuum is. The continuum is actually just the ability to go up and down in scale, but keep the same geometric grid. But in shapes that are weird like this, if we add more points into the shape, you're going to get, here there's like a trapezoid, and then if you add another couple of points, maybe it becomes a pentagon or some octagon or some unnameable shape that you don't want to know. So the adding points to these types of things, which is what we see in data science, that is not easily understood. It's not easily understood, but yet you can teach it to kids in high school and they will start to habitually get it. And then they gain a window into what do statisticians do? What do data scientists do? What are all these people at the beginning inventing new subjects that are going to be brought down the pipeline with AI? How are they seeing these data sets? What intuitions are they using to shape their thinking in the data sets? And the answer is they see it in terms of higher dimensional geometry. They're seeing these grid networks, but you can actually see like a sphere or a hyperbola inside of this stuff. I'm not going to show you how to do it, but hit me up later if you want to know. I don't know. Anyway, so what does this mean for math? So we can represent more possible spaces in math with finite graphs than we can represent with the concept of continuum and the concept of infinity. Now, any of you guys who've ever taken calculus knows that infinity plays a major part in calculus, and calculus is celebrated as like Isaac Newton and Leibniz and the pinnacle of this or that. But it's an ideal concept. We can do away with ideal concepts, and we can just return mathematics to what it was called originally, rocks. Just collections of rocks. There's different ways to operationalize infinity, but as a programmer, you can kind of create an infinite chessboard, if you will, just by creating a buffer overflow condition to handle those cases when you move off the board. You can just create more board. So there's different ways to get around it. This is just an example. Doesn't need to talk about it, but like on a chessboard that goes forever, you can have a mate in infinity, except it's not a mate in infinity. The idea would be that no matter how many squares this black rook moves out of the way for the king to avoid getting checkmated right here by the queen, the white side is going to have that many moves to eventually catch up with that other side. So black can pick a number like 10 to the billionth power, but white will eventually be able to checkmate that king. But because black can choose its number or its move before white has to then make a decision on how to checkmate black, we technically have a name for this kind of infinite number of positions, and it's called omega. So this is, again, don't think of it as infinity as like it just goes on forever. It's more of like a computer code that lets you bypass or lets you categorize or bypass particular game states. We'll talk about that maybe in another talk. So what does this mean for academia? If we change the way we teach math, any subjects whose adherents either envy mathematics, social science, or historically derive from mathematics, philosophy, some forms of law, not yours, Curt, but must make the shift below in their worldview, from the continuous to the discrete, from the idealizable to the realizable, okay? And then the rest of it is kind of like vocabulary that I think you would be familiar with from studying natural law.
You know, that's really the point, right?
This is the point right here. We got to make this shift.
This is the whole point is that's math as it was invented as language, and this is math as practiced by computation as operations.
Yes.
So that's the ideal and the real.
That's right.
It's that simple as we need to teach math as real. And one of the things that I think people aren't aware of is that we had geometry as our frame, the real. What happened was when we got algebra, it made it language
Took
again.
over.
And then when we got Descartes, he made it science again. And then when we got Einstein and Bohr, they made it fucking language again.
Yes.
And so we're all, you know, how many of us understand this?
I think there's like 15 people in the world that
Right,
that actually spend time on the toilet thinking about this stuff, like me and you, and
But it's, you know,
potty talk.
You're going to get to this in a minute, I know, but it's so profoundly important.
It's important.
It's like thinking, it's the difference between there's gravity and there isn't.
Yes.
I mean, it's huge.
This is enormous. In the academic context, I mean, academia, I kind of get it because I'm both an academic and I'm not. I live in the real world too.
You mean
But
you're just a nerd?
I'm just a nerd. Go to the wall nerd, as Curt put it one time. But, you know, we're all real people with real problems. These imaginary numbers are not going to solve my real problems unless it's designing a video game.
Well, you and I've talked about imagining numbers is the hack to make up for the fact that the math has conflated the dimensions.
Conflating direction and quantity.
And quantity. And
Yes.
That's just like, well, if you didn't do that, it wouldn't be a fucking problem.
That wouldn't be a problem. Yep. And so, but here's the thing. What I've been showing you guys is actually up to graduate level school mathematics. But you can teach this all to kids in a very practical way because they're playing with a video game or they're playing with stone arrangements. So, and also something that I didn't include in my talk because I'm not going to have enough time to do it. Numbers are actually a subset of games. So what a number is it's a game position where one side has an automatic win, regardless. It's a war of attrition. One side's going to win, regardless. But if there's a move advantage to either position, like if I get to move first, I get to win, but if you move first, maybe you win. That's called a hot game. Not a cold game, but a hot game. And numbers are a subset of all possible game positions. So one way to branch away from numbers is to branch into two-player and multiplayer games. I'm not going to talk about that today, but if you want to teach kids mathematics, a game of poker can teach them probability. A game of chess can teach them to sit down and think. You know, there's ways to teach kids that are not just running them through rote computations, algebra and all that stuff.
What you're saying is we tell the story of math as individual sets of analogies.
Mm-hmm.
And so what's happening is that nobody's actually understanding what they're doing, right? It's just like, this is how this kind of thing is done.
You put it away, sir. You said that math is a collection of dentist tools. And you have to know which exact tool to use in which situation. And then the stories sort of keep everybody gluing those tools together and sort of celebrating math. Math is the language of the universe. You know who said that? Galileo. He wasn't wrong, but he wasn't right either, because you have something closer to the language of the universe. I'm just moving along because I know we're short on time, and I'm having fun. So math lies to us. There's hidden costs, there's decay of state, there's time, there's agency. Right? There's no cost to hold state in mathematics. The pile of stones lasts forever. That's why they call them calculus. They wanted the things to represent things that lasted forever. Stones, back in ancient Greece, would pretty much last forever. Quoting Moritz Björling, cost of persistence. Changing state. To travel a distance from one thing to another, there's a cost. To acquire information in any subject, there's a cost. You got to Mess around and find out, as they say. And in math, you don't really mess around that much. You need a piece of paper and a pen to do it. And also adding new axioms or adding new dimensions. You don't introduce incommensurability when you do that in mathematics, but in other subjects you do. Imagine if the Supreme Court, or let's just say a new constitutional amendment were passed, that introduces a ton of incommensurability with prior law that now has to be adjudicated in courts. In mathematics, they're just like, oh, you need a new dimension? Here, perpendicular, stick it that way. Don't get any ideas from what I just said. So time doesn't exist in math. Also, the number of players in a game, I just alluded to that with games earlier. Math is a 0-player game. Computation is a 1-player game. So, yeah.
I just don't know. So what you're laying out here is that the number of dimensions of reality are being subtracted.
Yes.
To produce the, is that what you're getting?
Yes.
To? Okay.
Yes. And you're gonna love where this talk eventually goes, Curt. It's gonna be. So if this is important. Everybody wake up. Sorry, I told you to go to the bathroom and get a beer. Mathematics immaturity and the imitation of methodology. So there's no cost to hold state. Well, I've listed that already. I can change A into B. I can convert 2 + 1 into 3, but it doesn't take any effort in a mathematical context. But when you take kids out in the field counting cows and sheep, they actually have to put a stone in the bucket every time they see a cow to keep track of it, and then they have to combine the buckets and carry the buckets and get a glass of water because they're thirsty, right? So, but then, this quote, Galileo, math is the language of the universe, with emphasis on you. In a solipsistic way, you could think that. But it isn't. Math is the most numbed out simulation possible. Notice the word number. Numb. It's been hiding in plain view all along. So statistics describe stones arranged in space, the place of the things that you're measuring. Math never talks about anything alive. This is kind of an analogy here, but Hades is the king of the underworld. Maybe Hades is the king of mathematics. I don't know. Because you're studying dead things. You're living in the underworld. Nothing moves. So based on the way we teach kids mathematics, we teach them that reasoning means thinking in a way where there exists no cost to hold state, no cost to change state, no cost to travel a distance, no cost of acquiring information, no cost to add axioms or dimensions, and then you get good at these things and you're told that you're smart and you're going to go to college and you're going to get a good job. That's what we teach kids in school. Math does not punish or reinforce against this immaturity, and yet it stands at the top of the academy. It's a very strange thing that a subject that is so applicable and so useful has so much immaturity baked into it. And I made this little comment, why is only math and music have prodigies? Maybe it's because you don't actually get matured by math, and so therefore you don't actually have to be mature to be good at math. Sorry, guys.
You're saying something really profound here.
Yeah.
And I don't know, it's like when we said that, when I said that, well, we start with the Greeks, then we go to the language, or then we go back to the Descartes, and then we go back to the language, right? This really fucks the world up, right? Precisely because it is. And what you're saying is, if we want to make everything coherent, we have to make it we have to keep it all real.
Keep it all real.
Right, and so the problem is the left has all these violations of the laws of nature baked into it. And so they love this crap, right? And the problem is...
Most mathematicians are leftists, by the way.
But the problem is, you and I can discuss, we know this stuff, right? But I mean, you can't even I don't know how many people in the audience understand what the fuck he's talking about, right? So this is actually quite profound about how a simple idea that gets into the academy propagates through all other, quote, sciences, and you end up with non-science.
You're right. There's another very simple idea that has traveled for thousands of years, which is that of, like, let's say Christianity or various other religions, Buddhism. They started with simple ideas that improved your mindfulness and your sense of a social obligation, your social contract. These ideas and institutions and now around them have lasted 2,000 years. So has the academy, so has astronomy, so has mathematics. So we've been teaching things upside down for 2,000 years. I figured that out from reading Curt, and there just has to be more people describing this who know the technical side of mathematics that they can teach other math educators to change it, to turn up into down and down into up.
I think sorry, because I have to follow you, and it's going to suck, because you're good and you're fun.
Oh, come on.
All right, so
you're going right after me?
I think so. I have to go.
Not
right
Bryan? All right.
Who is it? Who's next?
You got you.
I go. So
10 minutes.
All right, I can make it.
All right, I just the whole point.
I'll make
this
it.
is really profound.
I'm going to speed run it. The slides will be up online, so you guys can look back Leftist logic examples, but it applies to rhinos too. Why can't we all chillax and get along? It's not that hard, right? The translation in operational terms would be everyone should be able to imitate an ideal form, chosen by me, of course, the philosopher king, or queen thinking this right now, and simply by imitating such forms, cooperation will be ensured. And also another thought that is in the same brain, why can't people just be themselves? Translation, no one should ever experience the cost of adaptation, especially adaptation to social norms that confer both individual and collective advantages, which is negentropy for nerds, to the group, let alone prevent harms, specifically non-fungible harms like death, because you can't buy yourself back from death. So also notice the so like, how everyone says like in conversation. I believe that's an equal sign subconsciously, because math confuses things with the equal sign. And so we are trying to get at what we're saying, and we've been taught, well, you can say this is like this, like this, like this, because that's association, that's free association. It's not identity. Yep. So, all right, what does this mean for academia if we change math? Well, the subjects themselves will go from continuous or ideals to discrete. It goes from nouns to verbs. We stop studying the nouns of a subject and getting interested in what describes the identity of something, but instead we move into a recipe of operations. How do you build something as opposed to describe something? All of those blank studies courses are just all noun-based. It's all in-group signaling, how we know that we are the things that we say that we are and that we are not in our behavior, but we actually are in our feeling field. Equality, which is presumed, gets turned into verification. So every time there's an equal sign, you have to say that there's a test that's being applied.
Can I, if I were to give you one bit, it would be survival.
Survival, yeah.
Instead of verification.
That makes sense.
Verification is part of the philosophical justification.
Do what he said.
It should be survival.
Should be survival, persistence. Cool. So where did idealism lead us in academia? And I have a painting, very famous painting, because I love art. I know Curt loves art. And this painting is called, is by Hieronymus Bosch, and it's called the 1960s and early 70s. And you can see what happened. Actually, I think it's the 50s on the left panel of the triptych, and then the 60s at the middle, and then this is like the Carter years in the 70s. This is the malaise after they went off the gold standard. You know, I don't know. Don't ask what. I don't know. And it's incredible that this guy knew this in 1500 and knew how to describe it. I love this painting so much, I just want to leave it up, but I got to move on. Taxonomy of subjects. So now let's get back to the original point I made. How do we redesign the academy? I want to say that I'm not done with this work. I'm inviting anyone to come in and contact me if they have better ways to organize this. But I'm bringing back the marginal costs per unit operation per subject. So I have to bring up this idea of a six-dimensional graph. I believe, from what I've looked at, there's 6 different ways in which you can add costs to operations or add numbers of people or intercepts or interrupters in a particular game state to go from the subject of mathematics to any other subject. So let's look at those. Cost to hold state, cost of persistence or survival, which is about memory. Does the state get remembered? Cost to change state, cost to acquire information or measure something or interact with it, cost to add ideas or axioms or dimensions, the number of agents, also the number of players in the game, and predictive accuracy. All of these things, I put map minus territory. I should have said map minus territory is equal to the inaccuracy. It's a measure of the inaccuracy, but you could say predictive accuracy or stability of prediction. So astronomy has a very high strength of prediction because the planets are moving in circles roughly and they don't change their orbits. Whereas in biology, you know, a lizard can just grab the thing that you're trying to experiment on and then the experiment's over and you got to run a new one. Where do you think math measures up as a subject? I think it's 0. I think it costs nothing to hold state, nothing to change state. The minimum amount cost to acquire information. Cost to add axioms is actually negative. The more axioms you add, the more robust your mathematical model. So you actually gain things by adding new laws. Number of agents, it's either 0 or 1. If you design the board game position and run the program, that's a 0-player game. But if you actually are intercepting the program as it's moving along, that's a 1-player game. And if there's someone else hitting a ball back at you, that's a 2-player game. Predictive inaccuracy, I changed it on this slide. So those are 6 different ways in which we can generalize from, or sorry, discretize or concretize from mathematics. So in this giant 6-dimensional box, math is the bottom cornerstone. It's trivial, it's universal, and it's trivial. It's the most trivial form of transcendent knowledge that exists. Now let's look at physics. Cost to hold state is small. It's not 0, but it's small. Atoms last 15 billion years about. Cost to change, protons rather, last about 15 billion years. Cost to change state is energy. Cost to acquire information is pretty low. Cost to add dimensions is low. Cost number of agents is still 0, 1, just like math. So math and physics are very similar, therefore, and they just overlap because they're both 0 or 1 player games. And the predictive inaccuracy is pretty low. That's known as the p-value, by the way, if you study statistics, p-value in a science. Then let's look at chemistry. I'll move through this fast and I'm almost done. Cost to hold state, it varies. Cost to change state is energy. Cost to acquire information is high. Adding axioms and inventions. When you introduce a new chemical theory, you have to rethink the whole periodic table, so it's a high cost. Yes, you have to now go through the adjudication process of do these theories match up together and why don't they? And then the predictive inaccuracy is medium. No chemistry experiment has a perfect efficiency. The Bessemer process to make steel, I think, is only like 90% efficient. Biology. Cost to hold state is actually the cost of survival. It's impossible to just to quantify that with a number. We need new measurements to even understand survival of biology. So we're adding all these new costs to hold state. Cost to change state, you have it up here. Cost to acquire information, and so forth. I would say biology is not merely more complex chemistry, because biology has players or agents in the game trying to change the game board that you're running a simulation on. So you can't jump ahead or calculate in biology, you can only compute. That's back to what Martin said about evolutionary computation. You have to run the simulation to get to the answer. You can't calculate or skip steps using logic. By the way, logic is a negative 1-player game. It needs a game board on which to operate. So that's a weird and esoteric idea, but there it is.
Freaking awesome.
Thank you.
I'm a nerd, though.
Yeah, I know you love it. That was for you, Curt, because I love you so much. Astronomy. Cost to hold state is more like mathematics. It's near 0. Cost to change state, I can't change the motion of a planet. So it's not applicable.
Infinite.
Yeah, infinite, right, infinite. Cost to acquire information. Cost to add axioms is pretty low. So you can see astronomy here. It's almost physics, but with far more stability of outcome. Planets are predictable. The flames on your stove are not. They're predictable in the aggregate, but not predictable in the instantaneous. And then we have economics. Economics is kind of like math, but it's an infinite player game. It's now when everyone's a player. And also there's the cost to hold state is non-zero, but it can be quite low if you can store things. But you can't store services. You can't store people. Well, that's called slavery, I guess, but it's immoral. Cost to change state is non-zero, but if you make money more fungible, now we can exchange things that were previously incommensurate. And the cost to acquire information is simply what we call the price discovery. Oh, look at this one. Look at this subject. Oh, interesting. What's this called? The Natural Law Institute. Everything's high with law. Like, it's the highest. I'm arguing that law is the highest cost subject to do anything in, because you're affecting so many people in so many ways, and you're prescribing behaviors to people over the longest period of time. So you see what I'm showing you? Law is the opposite corner of the grid to mathematics. So if mathematics is the hydrogen of the periodic table, law would be like plutonium or uranium, way down in the other bottom corner, with the highest level of complexity, highest cost per transaction going on. And of course, all the other subjects in the academy that are valid should fit into the rest of the grid, where you can make a simple, you can describe how these different costs go from low to high along each of these 6 axes, or maybe 7, or maybe 8. And I'm sure there's a way to break these down into 3, like a triangle, but there'd be subgroups of costs within that triangle. So, yeah. So, periodic table of subjects, why is this useful? Well, we can predict new subjects. There are maybe subjects we haven't discovered before. And we can also see that law is the furthest valid subject from mathematics, highest possible cost to build, maintain, and run a legal system. It's like biology, but with regard to non-fungible costs. It's unlike an economy, which allows for more fungible costs. And then we have law, thanks to you, Curt, remains commensurable with mathematics. So Curt found a way to make, through ordinal logic, you can go from mathematics all the way up to law and back down. So even though you cannot reduce law to mathematics, you can commensurate law with mathematics, and that's what I'm trying to argue today. And no subject in or of the academy can go further than law on all 6 or 7 or whatever of these axes. So if you can't account for yourself in any one of these 6 dimensions, you're kicked out of the academy. So maybe something like literature would stay in the academy because
I didn't see that coming.
Yeah, thank you. So maybe literature stays in because you're trying to teach people norms and values and maybe ideals to imitate. I'm going back to that.
You're evil.
Yeah, I am. all admitted subjects are commensurable with mathematics and with natural law. So if you can't commensurate with either subject, you're probably suspect. You're sus as a subject.
I like that. So you've said there's we can get to what you're testifying to about, but even your the construction of your discipline is dependent upon these. That's fucking brilliant.
Yeah, we'll talk about it. We'll talk about it.
That was sexy, dude.
Thank you. Esoterica, I'll run through this quickly. The negative, it's also possible to have a negative dimension. It's just the empty space. We call it the negative space. So the negative space of games is logic, because it's waiting for a game to be applied to. And Curt figured that out. So anyways, we got that. I think that's actually the end of my slides. And I don't really have anything else to say other than I wanted to go into a whole talk about how numbers generalize to game positions. We don't have time for that. I don't want to play games with you folks. We're here to do serious things. So my name is Michael Surrago. You can get my contact information. Just come up to me and talk to me. I'm not like that fancy. And it was really an honor to be with all of you. I appreciate so much the chance to do this and to be with all of you. I flew in from Hawaii to see you all. So much love. Thank you, guys.